So let's look specifically at some of the processes that typically are not considered when we do equatorial wave theory. One is the dissipation, especially the one associated with convection. Convection is a turbulent process. Turbulence is dissipative, so there is cumulus friction, which is now more commonly included explicitly in parameterizations and so on. We'll see if we add friction. CP Chang showed that you generate a fast mode and a slow mode. Uh, Changes in vertical stability associated with convection is also not always included. We talked about this in the Chani conundrum, where he said convection tends to reduce stability and that allows the baroclinic processes. And there are also interactive surface fluxes, which we mentioned before for Togacore, Jasmine, and so on. We'll come back to those again when we do other processes of convection. Convective dissipation then can be included in the wave equation. We just recap our original governing equations of x and y, momentum equations, hydrostatic balance, the continuity equation, and the thermodynamic equation with the heating term included in here, and the vertical stratification, of course. We sought normal modes in longitude and time in this form, the real part of the solution with the exponential component. For Kelvin wave, we just set v equal to 0, so you end up with Doppler shifted frequency in terms of gravity, wave speed, and k, the zonal wave number. We have the meridional structure in terms of beta and frequency and wave number, and you have the zonal speed associated with the wave given by this with v equal to 0. Okay, you add friction to the linearized wave equation. We have the horizontal momentum equation with the convective friction, the geostrophic balance, vertical hydrostatic balance equation, and then you have the thermodynamic equation with z defined in terms of the vertical scale height, and the vertical velocity is dz dt. So with frictional convergence, you're going to have vertical velocity. Okay, so you have to remember that. Basically, near the surface, if there is frictional convergence, you add Coriolis and you end up with a cyclonic circulation with the convergence in the middle, and since velocity cannot go down, it goes up, which gives us Ekman pumping and so on, that we will look at a little bit later on. So you have the frictional damping in here in the vertical equation as well. Okay, so we are looking for u and geopotential as a function of proportional to exponential minus beta y squared over 2 c hat, where now c hat, because of this friction added, is a complex function. So you have a complex entity. If f is 0, we end up, of course, with the inviscid fast wave. The vertical velocity perturbation associated with the vertical propagation can be written this way in terms of Wz. So then we write the vertical wave equation in terms of m squared, which gives us the relation between m squared and the stability parameter, the complex zonal wave number, and the mean depth. We will see in a minute what happens to this when the mean depth is in a certain range. So q hat here is r over cph e to the minus z, or 2h with this q that we looked for eigensolutions in the previous equations. The vertical stability parameter given by this vertical structure function. For any vertical wavelength much less than 88 kilometers, the relation between zonal and zonal group gravity wave speed and vertical wave number is s to the 1/2. C is complex and this is real, so obviously M has to be complex as well. So M can be written as real plus the complex part. You can do some manipulation and get the equations for the gravity wave speed for mode 1 and 2 instead of in terms of the vertical structure and vertical wave numbers. Remembering that if f goes to 0, then we just get the one mode, but generally the forcing dissipation can force both modes. So convection associated dissipation can force both modes, so you end up with this equation for the vertical wave number mode 1 and mode 2. Okay, so there is the real vertical wave number, and that's the complex vertical wave number. We had seen before that we had, when we looked at the cloud top temperature variance, we had the spectral, in the spectral phase wave number frequency diagram, we had the westward internal gravity waves, equatorial Rossby waves, and Kelvin waves for various equivalent depths. MJO was down here, so we have to look at that again. But we can, in the meantime, look at estimates of the impact of convective dissipation on equatorial modes with various damping timescales going from 3 days to 10 days out to infinity. The main thing you see, and this one is plotting imaginary vertical wave number versus the vertical scale height. Okay, so the phase speed is not seriously affected by the damping scale for the fast mode, whereas the slow mode is greatly affected by the damping time scale. Okay, you can see that of course this is a slow mode, so you can see phase speeds, Doppler shifted phase speeds are slower than the fast mode. Okay, so the fast mode is less affected by the friction, which is why it's fast, and this is the regular mode. Imaginary component of the phase speed again as vertical scale height. Again, you can see that the damping scale affects the first mode very little, whereas the mode 2 is distributed over a wide range based on the damping time scale. Okay, that's so the forcing can generate both modes, and damping scales greatly affect the slow mode, the viscous mode, and not the fast mode. So that's the brief introduction to the fast and slow modes when you have convective friction. Okay.